Hello, everyone. Welcome to the fourth day of Understanding Deep Learning. This event is organized by Data, a student data science and machine learning at the University of São Paulo. My name is Theo Riffel. I'm a computer scientist and a coordinator of data. I'd like to thank the University of São Paulo and ICMC, Institute of Mathematical and Computer Science, for the support and help in promoting this event. I would like to give a special thanks to Marlos for accepting our invitation. We're very excited to have you here. Our speaker today, Marlos Machado, is an assistant professor at the University of Alberta. His research interests lie broadly in machine learning, specifically in deep reinforcement learning, representation learning, continual learning, and real-world applications of all above. He is also an Alberta Machine Intelligence Institute Fellow, a Canada CIFAR AI Chair through AMI, and a principal investigator in the Reinforcement Learning and Artificial Intelligence group. He completed his bachelor's and master's at the Federal University of Minas Gerais, Brazil, and he has his PhD at the University of Alberta. Before becoming a professor, he was a researcher at DeepMind and at Google Brain for 4 years. During which time he made several contributions to reinforcement learning, including the application of deep reinforcement learning to control loose stratospheric balloons, which was published in Nature. His research has been featured in popular media such as BCC, Bloomberg TV, The Verge, and The Wired. Before we begin, I'd like to give a quick disclaimer for our Portuguese-speaking audience. Oi, gente, tudo bem? Essa palestra vai ser ministrada em inglês, então caso você tenha alguma dificuldade de acompanhar, fique tranquilo, todas as palestras ficarão disponíveis no nosso YouTube, no YouTube do ICMC TV, e em algumas horas a tradução automática vai ficar disponível para vocês. E a tradução automática do YouTube tem melhorado muito esses anos, então espero que vocês consigam acompanhar por lá. Now, without further ado, let's hear Marlos. Welcome, Marlos.
Thank you very much, Tal. Thanks for the introduction. I'm always embarrassed by these long introductions. People ask for a bio, and then you suspect that this is going to appear only in a website, and then someone say them out loud, and then it's long. Anyway, thank you so much for having me here. I'm very happy to be able to give a talk. I apologize for the Portuguese-speaking audience, but I'll give the talk in English. But just as a housekeeping, if anyone wants to ask questions in Portuguese, I'm more than happy to take them. I can translate them for you, for the rest of the audience, and then I'll answer the question, okay? During the talk, if you want to ask questions, you should feel free to write a comment, and then I'll do my best to try to monitor the chat to answer questions. I have to say that I'm a little bit nervous. I think it's the first time that I'm giving a talk that it's actually being live streamed on YouTube, but let's see how that goes, okay? So, on the theme of understanding deep learning, the topic of my talk today is going to be about revisiting the fundamentals of deep reinforcement learning for learning continually. I know it's a mouthful, it's a fairly long title, and I'm going to parse this as we go along, but it's basically the main gist of this talk is that I want to talk about how we get to have systems that actually learn continually instead of being deployed. And if we want to do this, and we want to do this with reinforcement learning using neural networks, finally deep learning comes into play, we're going to have to revisit some of the things because the standard machinery that we have for deep learning doesn't seem to, and reinforcement learning in general, doesn't seem to be very applicable to continual learning problems. Okay, but let's start. So this is the summary of pretty much the last year or so of my research in continual reinforcement learning. So you're going to be seeing pretty much papers only from 2023 and 2024. And every time that I have a paper that I'm talking about, I'm going to have the pictures of the students that were involved in the project. If there are other PIs, I'm not showing them. I just want to show the students who participate in this project. And if this is kind of a TLDR, the continual learning, if you want to do continual learning, I want to argue that it's pretty much required if we want to actually tackle large problems. And which means that this notion that we're going to have a system and we're going to train a lot of data and then we're eventually going to deploy that system, it's not, there are many problems that this is not going to cut, you know? And the other thing is that this talk is about deep reinforcement learning, not reinforcement learning in general. So this is really thinking about what we get out of the deep learning, the effect that we're combining deep learning with reinforcement learning, okay? Um, and basically what I'm going to argue today is that we need to revisit the fundamentals of deep reinforcement learning in order to succeed in deep continual reinforcement learning. And the problem is that if we look at traditional RL agents, traditional deep RL agents, when they are learning continually, they struggle to assign credit properly because they lose their ability to learn. They can't deal with changes in the environment when exploring because their knowledge isn't reusable. And the representation that they learn, they generally are not well suited. And by this, I mean they generalize poorly for fast adaptation and model learning, which are things that we would arguably want to have a continual learning agent to be able to do. Okay? One more thing that I want to say is that I used to give this talk in a shorter time slot, which is 30 minutes. And then I say, oh, I will do this quickly. And I'm going to go over many results on a high level. And then I had two options here. I could slow down or I could add more stuff. And surprise, surprise, I decided to add some of the recent results. So I will still do this somewhat quickly in the sense of like a lot of the plots that I'm going to have, they're visual cues for me, not for you. So but the reason I'm saying this is because I want you to make sure that you pay attention to what I'm saying, and the plots are going to be just supporting the narrative. Okay, and the main structure of this talk is going to be that I'll show that there is a problem, then I'll briefly talk about one or two solutions about that problem. Okay, so first and foremost, what is reinforcement learning? So reinforcement learning is this paradigm in machine learning where we have that it's inspired by animal learning. And the idea here is that we want to have a system that learn by interacting with the environment. We want to have systems that learn by trial and error. It's very similar to how we learn, I would argue. You know, like we are operating in an environment and we do things that seem good, that feel good. And because of that, what do? We try to do more of that. And sometimes we do things that are going to hurt, and we learn to avoid doing those things. You know, like we just learn by interacting with the world, and sometimes we need to do things that are not pleasant because we're anticipating that something really good is going to happen later on, and stuff like that. The way we formalize this in reinforcement learning is that we're going to say that we have an agent interacting with the environment. So this interaction is going to take place in discrete time steps, and at each iteration, this agent is going to receive an observation, what it's seeing, you know, like, and a reward that is just like how good it is the thing that it's seeing. And then the agent is going to take an action. This action is going to impact its ability to, it's going to impact its environment, and the agent is then going to receive another observation and another reward. You know, and this is how this iteration is going to go. So this is very similar to how we train dogs, for example. You know, like how do we train dogs? We tell, like, if we want a dog to sit, the dog is there, and we say sit. The dog received the command as an observation, and then the dog takes the action of sitting. And as the dog takes the action of sitting, we want to reward that dog that action, so we give them a treat, and they learn by just being reinforced, by having the right behavior being reinforced. You know. So this is standard reinforcement learning. This is to tackle what we call sequential decision-making problems, which are problems that we have to make a sequence of decisions before we see an outcome. And I would argue that when we are talking about sequential decision-making problems, we always have to do with three things. We have to do with credit assignment, exploration, and generalization. And let me tell you what I mean by that. For credit assignment is this notion that we have to be able to answer the question, what was the key thing that I did right or that I did wrong? What, like, if let's say that you're playing chess, what was the winning move? You know, like, very rarely the winning move on a chess match is the last move. Halfway through the game, you're going to do something that is awesome, and then you're going to realize that, oh, this is the thing that allowed me to win the game. But how do you figure out as an AI what was the key thing that led you to the outcome that you're observing? You know. And notice, this is fundamentally different than things like supervised learning, right? Because we don't have this delayed credit assignment problem. We also have to do exploration because we don't have data sets. we are interact with the world, right? So basically, we have to be able to answer the question: how do I generate data that will accelerate learning? I need to learn how to, if I want to learn how to play chess and how to win in a game of chess, I need to first realize that it's possible to win. So how do I generate data that's going to allow me to win and stuff like that? And finally, we have generalization, which is that when we think about really big problems, we rarely see the same thing twice. Imagine that you go to a different city. You've never been to that city before, but you still know how to drive in that city because you can generalize your experience. So the real question about generalization is, how should I react to things that I have never seen before? And and the main gist of this talk is to say again that we struggle to do these three things when we're wanting systems that learn continually. Um, and the reason this is a deep reinforcement learning talk is because 10 years ago or so, there was this paper that introduced this notion of deep reinforcement learning that was to use neural networks to tackle this generalization problem. Okay, and this is the what we're going to start with, this notion of using neural networks to tackle this type of problem. So the catch, though, is that this is the diagram that we show in reinforcement learning. If you read the reinforcement learning textbook, you're going to see that this is how we talk about things. But I would argue that this diagram is a little bit misleading when we talk about deep reinforcement learning. Maybe a much more accurate diagram would be this. And what I mean by that is that the agent, our system, our learning algorithm with a neural network and so on, it is much bigger than the environment. And what I mean by that is that, like, let's say if we go back to the paper from 10 years ago, I'm not even talking about the modern papers, but 10 years ago, we had a convolutional neural network that had many, many, many parameters, millions of parameters, to be able to play an Atari game that would fit in 2 kilobytes, 4 kilobytes of RAM, depending how you count the cartridge memory as well. So in a sense, our agent, quote unquote, the brain of our agent, is actually much more complex than the environment. And this is a little bit misleading because what I would argue is that this is actually a much more representative way of how the world works, right? Like the agent is tiny given the complexity of the environment. We as humans, we are unable to capture all the complexity of weather patterns, of all the molecules that are going on, everything that exists in the world. So in a sense, because the world is so complex, there is no way that we can learn a fixed policy, we can learn a fixed function and say that this is always going to be applicable, because this function unavoidably is going to be wrong because it doesn't have the capacity to capture all the nuance of the environment. And maybe you don't buy this argument, but maybe one way to think about this is, imagine that you're going to have at least other agents that are as big as you in the same world. Like my brain is as big as the brain of any people watching this talk, which means that my brain is not able to model the brain of every single agent. So the same applies for artificial agents. Like if you're going to think about having other complex agents in the world, it's impossible to model everything that they can do. So we have to adapt to them. So basically, the gist here is that agents need to learn continually because they need to be constantly adapting, like we do. And let me give you an example. This is an example of a project that I worked here, which is to look at a water treatment plant. So what we wanted to do was that we wanted to be able to predict the properties of the water that was coming. So basically, the water is coming down the hill in a river, and we're looking at that water, and we're going to throw some chemicals in that water to be able to make it drinking water. And this was done in Drayton Valley here in Alberta, in Canada, which is kind of a weird country because different from Brazil, the water freezes for a big chunk of the year. So because of that, we have a lot of variability on the properties of the water. What I'm plotting here is this. These are the three curves. Sorry, this is like three different properties that we're measuring, like the pressure of the membrane of the station, the turbidity of the water, and the temperature of the water. Like the temperature is pretty easy to see, right? Like you see that in the winter here, basically it's going to be cold, and then at the spring eventually it starts to go up. The summer it's warm, and then in the fall it starts to go down, and then it's cold again in the winter. this is like just to show this. And there are many things that we don't control in this plant. For example, every now and then an operator might come and install a new membrane. And when the operator installs a new membrane, what can we do about that? We don't know that a new membrane is coming. All we have to do is to adjust, there is this weird season, which is called the freshet season here, which is when the snow is melting from the hills and it's going down the river. And then there is a lot of extra things like dirty that comes in the water. So you can see that the turbidity of the water really spikes and stuff like that. And it's really hard to predict all those things. And we wanted to be able to predict these properties of the water, because before we can make any type of control and taking actions in the system, we need to be able to predict what's going to happen. And basically what we did, and this is just to demonstrate the point, is that we trained the agent offline on data from, let's say, November 1st to November 23rd. So the first 3 weeks of November. And then we tuned the hyperparameters on the data from the last week of November. And then we deployed that system for a 7-day period in December. Like something very traditional. You train for a while and then you deploy the system on when you can. And we looked at the performance. And basically what I'm showing here is just like, first, this black curve here is the signal that we're trying to predict. Okay, this is the actual temperature. And early in deployment, the purple curve, this is the performance of the purple curve when it's in the learned model. Meaning, we trained on this data and we deployed the fixed model. The blue curve is what we get if we're learning continually. Guess what? We get the first week of December. It's fairly different than the first week of November. And because we're adapting online, we can actually track that signal much better. And this is early in deployment. Late in deployment, you can see that things get really bad because we're way off in terms of the learned model would predict. But we are actually able to track that much better because we're being able to learn that online, And this is just, in a sense, trying to convince you of the importance of being able to learn continually, which is not, in fact, the main paradigm that a lot of people are doing in machine learning. But I would argue that it's very likely what we're going to move more and more towards in the future. And in a sense, a lot of these big companies, they're starting to talk about how they want to be able to learn continually, and this is one of their priorities from the time being. So now let's go back to this notion, okay, so there are this, okay, hopefully you agree with me, or at least you don't have a knee-jerk reaction that this is a bad idea, that maybe we want to have the ability to have systems that can learn online. And then what I'm going to argue is that we cannot effectively do any of the things that we have to do in sequential decision-making problems. Because in credit assignment, neural networks lose plasticity, meaning that their ability to train, and then they are unable to assign credit over time. When you talk about exploration, standard solutions do not work when the world changes. And when we talk about generalization, the best approaches for continual representation learning, they are different than what you would get if you're just having a fixed scenario, So let me start with credit assignment to give some examples about this. So let's start with a paper that was published in 2018. It's a paper from DeepMind, and it was, at the time and pretty much until today, it is the state of the art on how to play Atari games in a single stream of experience. This algorithm is called Rainbow, and this is and basically what you can see here is that this Rainbow, this curve here, it's much higher than anything else because it can play these games amazingly well. But again, remember, this network that it's being used in Rainbow here, it's huge compared to what an Atari game is. So what we wanted to do was to challenge this algorithm and ask the question of like, well, what if the world was more complicated than just a fixed game? And what we did was that we had this agent, we created this notion of a switching ALE that basically the agent is going to start playing a game, and after a while this game is going to change, and after a while the game is going to change, and the agent is not going to be told when the game changes. All the agent needs to do is to be able to adapt. It's just a stream of experience that the agent needs to be able to do well when playing all those games, And in case you're not familiar, I'm using this the agent Rainbow here from My Little Pony because I have two small kids, so I'm very familiar with cartoons nowadays, and I wouldn't miss the opportunity of using something like that to refer to a Rainbow agent. So That's it, okay? So that's what we wanted to do. We just wanted the same, in a sense, very similar setting. I just want a deep RL agent, big neural network, to be able to play a couple of Atari games, but they're going to be changing, and you need to be adapting. And and when we do this, it isn't that we don't know how to learn continually, it's that we're actually losing our ability to learn. So let me walk you through this plot. So what we did was just say that, okay, so we're going to be playing 5 games, and let's say we're going to play these games, and every 20 million steps I'm going to change to a new game, and the agent doesn't know that it's going to change, you know. So when you start here, the y-axis is going to be performance and the x-axis is time. When you start, you basically, what happens is that you see that you're doing really well. Okay, you're learning, it's going up, you're happy. But then the game changes. And as the game changes, you're going to play other 4 games. And I'm not plotting the performance in those other 4 games. But what happens is that after all the other games were played, you will go back to that environment. And this is how well you were doing. So you have a big drop in performance. I would argue that this is not even so bad, this drop in performance, because well, maybe you have a limited capacity and you had to forget the other things to be able to learn new things. That's not the end of the world. But then what I would expect the agent to be able to do is to learn again. But what we see is this blue curve. If instead we had just reset all the weights of our neural network, and I like to make the joke that I'm lobotomizing the neural network, and just started fresh, we would get this gray curve. So in a sense, we had 100 million steps of experience. And that hurts us. It's weird. How can data hurt us when it's data literally from this same game, you know? And this just keeps getting worse. If we keep doing this over and over again, this keeps getting worse. But you have to be patient to see some of those things. Like these experiments, sometimes they take a month to run, and we actually wanted to be serious about it. We wanted to come and say, well, what if we ran it for long enough, as we would expect an intelligent being deployed in the world to be able to learn? And we see that things are not great, you know? To be fair, we're not the first ones to report this. In fact, this loss of plasticity phenomenon is something that just recently, a month ago or so, was published at Nature, the paper that pitched this. And it was a paper from some of the researchers here at the University of Alberta that did this. But we wanted to do this in a deep RL setting, and this is what we were able to show. But then, as scientists, here's the question. Why is this happening? It's weird, right? What's going on? So, some of the symptoms, and the why question is really difficult to answer, right? Because it implies some causality argument here that it might not be so easy to make, but we can look at some symptoms. So one of the things that we can see is that unit saturation is a really big deal. What do I mean by that? So if we look at the loss function, we're going to look at the blue curve is our continual learning agent. And if we just learned from scratch the lobotomized agent, this is what we would get with, it's the red curve. So the loss function, lower is better, you have lower loss. So everything makes sense. Here we have a worse agent, thus it has a higher loss. Good. But then things start to get tricky, because when we look at how much the weights are changing, what we start to realize is that even though the loss function is really high for the continual learning agent, the weights don't change as much as they change for the learning from scratch. And this is puzzling, right? Like, how can you have a loss that it's really big if and have the weights changing so little? And well, of course, the point is that the gradients, when we look at the gradients that we end up using to update the neural networks, they are way smaller for the continual learning agent than they are from the scratch agent. And the reason for that, when we looked at it, is because of the activation functions. So basically, what was going on is that we were using ReLUs, and they were saturating. So basically, we were just getting zeros as the output of the ReLU, and by the chain rule, 0 times a gradient is going to be 0. So basically, we're losing our ability to learn because of that, because that ReLU is basically saturating. So in light of that, we could mitigate loss of plasticity. So we looked at ReLUs, for example, which is like just a very simple idea, which is what if we added not only 1 but 2 ReLUs, which are like the opposite, the negation of the sign. You know, so if you have a positive value here, you're going to have the value of the ReLU, but if you have it negative here, at least you have it positive for another input. And when we do this, we are able to address this issue of loss of plasticity, to mitigate it, at least in this type of environment. But just to contextualize things here, we haven't fixed anything. We All we did was to say that, well, at least now we have neural networks that you don't want to throw away all the data, but all we're doing very little compared to if we were to learn from scratch in that single game throughout the time. So sure, we can recover the same thing as if we were seeing it fresh, but we're definitely not being able to leverage past information. And this is still a little bit unsatisfying, you know? So I have this PhD student, Alex Lewandowski, that he is really puzzled by this question of loss of plasticity. And, and then when we start looking at this more carefully, one of the things that we notice is that, and this is a result that has been reported, is that everyone knows that a good initialization on a neural network is really important, right? Arguably, this was one of the key things that allowed deep learning to actually happen 15 years ago. But then when we look at the properties of this good initialization, basically one of the things that we want is that we want the average singular values of the layer-wise Jacobian to be close to 1. And what we see is that over the course of learning, the singular values deviate from the initialization and they tend to grow over time, you know? And what we show is that the deviations from this initial singular value distribution can result in very low gradient diversity, which impacts our ability to learn continually. And what I mean by impacting this gradient diversity is that if you think about the non-convex optimization landscape that we want to have gradients that are pointing in all sorts of directions, because when the problem changes and we have to navigate somewhere, basically the gradient is able to navigate in that direction. But what happens is that as the singular values start to get, like, they start to change the singular value distribution, we basically start to losing this ability to navigate in some parts of the space. So we even wrote a paper talking about this in terms of a loss of curvature of the space, you know. So noticing this, we go back to the same old tricks that we always use in machine learning, which is to regularize. And what we did was to introduce this spectral regularization, that basically we're controlling the maximum singular vectors of the singular value, of the weight matrix of the neural network and of the bias term. And what you can see here is that, like, this is the orange curve, and these are like supervised learning problems that keep changing. And you can see is that this orange curve, it's able to actually do much better over time compared to pretty much all these other curves are baselines and other methods that people have proposed, you know. And in fact, sometimes we even see what we would aspire to get, which is the neural network being able to leverage past experience to do better than if it was just learning from scratch, which is pretty encouraging. This is also applicable to DeepRL. When we go to DeepRL and we look at some control tasks like these ones, and what we did in this case was to investigate this in a high replay ratio setting, which is something that has also been reported to have a lot of problems with loss of plasticity. Again, when we look at our orange curve, we can see that we can do much better than even something that leverages information about the problem, which are like constantly resets of the network, which again seems utterly unsatisfying, just removing stuff from the neural network that we have already learned, you know. So that's good. But you know what also what never loses plasticity? Linear function approximation. So if we do linear function approximation, meaning we're not going to use neural networks, we're just going to do a dot product between features and weights. If we do linear function approximation, what we can see is that we never lose plasticity. These are the gray curves, the green curves. But the problem, though, of course, is that we all know at this point that linear function approximation is not as powerful as non-linear function approximation to approximate complex functions, right? Like, of course, linear can only approximate linear things that are linearly separable. So in that context, what Alex did was to introduce this notion of was to leverage these Fourier features, but doing this across all the layers of a neural network. We call that deep Fourier features, which is the notion of, like, when I have a signal, what I'm going to look at is that I'm going to look at the sine and the cosine of that signal. The beauty of this is that because of how the sine and cosine functions, they are shifted a little bit from each other. For every input, every point in the line here, one of those two curves are going to be, if we look at the Taylor approximation, they're going to be approximating a linear function. So let's say here, in this interval here, we see that the sine function is approximating this linear function, even though the cosine function is giving us the nonlinearity that we would expect. But then if you shift that a little bit, then we see that the cosine function is the one approximating the linearity, while the sine function is giving us the nonlinearity. So arguably, this is the best of two worlds, because we can approximate the linearity, we can get the linearity, but we can also get the nonlinearity, And long story short, this also works, and we can see pretty good results in terms of how we're improving our system, and which leverages this linearity. So that's it. That's the first third of the talk. Let's put it this way. But the other thirds are faster, I promise. But it's this notion of like, okay, neural networks lose the ability to learn, and this has been well documented by us and many other groups by now at this point. And we start to have a hand of maybe how to tackle this. But that forces us to actually think about the continual learning problem and what happens out of these changing distributions in the optimization landscape and stuff like that. Now let's talk about exploration. So, I'm sorry. About the exploration thing, what we need to do is that we need to be able to find what is the solution by chance, so we can learn about it, And in reinforcement learning, we love grid worlds because they're easy to visualize. And I'm going to use a grid world to demonstrate this again here to give you better intuition. But let's say that you're this agent and you start at the top right corner here, and you want to go to the bottom left corner. You don't know anything about the environment. You don't even know that it has walls. So what we quite often do is that we take random actions until we stumble upon the goal, and then we start learning how to do this. Of course, we can do better than random, and we have developed many algorithms to do some of those things. Some of them are things like some notion of surprise. When I'm surprised by what I'm seeing, maybe this means that it's novel. It's the thing that I'm seeing is novel, so I should prioritize things that surprise me. Or alternatively, we could have things like counts. Let's keep counts of the number of times that I've been to each state. In this case, we're talking about pixels, so we can use some density model to do counts in this space. But then again, we want to go to places that we have visited less often, And when we do this and we say, oh, let's see if it works, this actually works really well. So what I'm showing you here is this. This is just like what you would get the orange curve if you were doing things randomly. The purple curve is what you would do if you're just trying to do some simple temporal extent exploration. The green curve is what you're keeping counts, and the red curve is some notion of surprise, But then here's the deal. What if we change the problem? What if halfway through, maybe you wanna navigate in a city and some of the roads are blocked, like this is not available anymore. And now you're starting from someone else's house, not yours, and you want to go somewhere else. How do you learn about this? And we're not going to tell the agent that the world has changed, because we rarely know when the world changes, And if we do this is what we can see the curves look like. You can see that a lot of those algorithms really struggle to do this. And while R&D, for example, which is a curiosity-based one, it still eventually it recovers, but it takes a while, And the reason is because, like, if you're keeping counts of the number of times you've been to each state and the world has changed, you don't get to know that, hey, maybe reset your counts. You don't know that the world has changed, Or if you're going to talk about surprise and how the world has changed, everything is surprising to you, and it takes a while for you to realize that you should adapt to that. But here's a different idea. What if we learned reusable skills which allow us to better navigate the world? And what I mean by that is the following. Imagine that you're in this environment, and instead of just trying to learn how to go from one place to the other, we learned how to go from one room to the other. We just learned, you know what? Given that I'm in this room, I want to have the ability to go to a different room. I would argue that we all have this ability, right? Like if we are in a building, and I tell you that you have to find where the free pizza is in the building, you are not going to be randomly going around back and forth in a corridor. You're going to try room by room by room, because this is the level of abstraction that we think about navigating. And what if we had that? The beauty of this is that when the world changes, these things are still reusable. Some of them might not be applicable because you see there is a it was blocked here, but the other ones are still reusable. And if we do this is the blue curve, we can see that we're actually able to do much better and actually adapt to these changes and recover from changes much quicker than pretty much all the other standard solutions that we have with theoretical guarantees for exploration when we're talking about non-stationarity. You know, uh, this is a topic that it's really dear to me. There is this notion, this notion of using skills for exploration, and there's this fundamental question about, well, how do we even learn the abstractions of rooms, and that I should go from one room to the other? I just don't have the time to talk about this. I have written many papers on the topic, but I wish I could tell you more. If this is something that you're interested about, maybe these are two references that are relatively recent that you should check it out, that are going to give an intuition of how we developed what we developed, including, of course, the reference from the previous slide that had the results themselves. Okay? But again, just for us to not lose the big picture here, I spent some time talking about how neural networks lose plasticity and maybe how we can use regularization, notions of different activation functions to avoid that. I have talked about exploration and how a lot of the standard solutions, they rely on some notion of stationarity. And when the world changes, that doesn't really apply. And maybe what we should be doing is to be thinking about learning reusable skills. That seems to be a tractable way for us to navigate the world and navigate MDPs and explore in general. And then let me talk about this last aspect here, which is the notion of generalization. Okay, so when we do deep reinforcement learning, basically what we have is that we have this this agent interacting with the environment here, and we're feeding, let's say, these images to convolutional layers or to other neural networks, and then basically all sorts of activations happen. And what we see here is that we eventually are going to start predicting how good each action is, or which action should take, depending on the algorithm that you're using. And sometimes we have these auxiliary objectives. We call them auxiliary tasks that are supposed to help us improve the representations that we're learning in the task. This is the standard way that we do deep RL. And for the longest time, what actually happened here is that before everyone was doing deep learning, people spent a lot of time thinking about what are the properties of good representation. Should we want sparse representation? Should we want representations that are orthogonal to each other, and so on? And when deep learning came to be, we pretty much said, like, well, trust your gradients. The gradient thing is going to find the good representations, and it doesn't really matter. You don't need to know anything about those properties of representations, but we were a little bit skeptical about that. And what we actually wanted to do is to monitor the properties that people thought to be good in the past. How much are we reducing the complexity of our space, or of our space? How sparse the representations are, how orthogonal they are, how aware of the dynamics of the environment, or how diverse they are, and stuff like that. And what we would do is that we would monitor the properties of those representations over time to understand what makes a good representation. And what it's interesting is that, again, if we start moving the goal state and we try to change where to go, some representations work much better than others. This is what I'm showing here. Like, you can see that it's not really relevant, but this VF5 that we're using here, it works pretty well across goals, because each one of the ticks on this x-axis here is the area under the curve for a different goal location. So basically, one of curve that it's doing well across the board. While if let's say you are not using any auxiliary task, you're just relying on your gradients, it starts to get really bad. And what we did was to start looking at the properties, and we noticed that there were some properties that were really good to get right. Some sparse properties, some representations that are sparse, that are orthogonal, that are able to reduce the complexity of the problem. These were properties that seemed really relevant and really helpful when we were changing these goals, which is not something that people necessarily are thinking about when they're talking about just solving a single problem, because as you can see, when you solve the single problem, you can do really well. The only problem is that you are kind of overfitting to that problem specifically, and to small variants around the problem. Like because in this x-axis here, the further you are from the origin, the more different the task is from the original task. So inspired by this, and we look at, well, it seems that we want sparse representations, we want orthogonal representations, and then we also looked at some of the recent papers that come that are not from our groups, papers like algorithms like Dreamer, that start to use things that we call like discrete representations. They use some notion of VQ-VAE or stuff like that, that basically are going to learn how to, basically you learn a representation that is continuous, but then you have this other embedding space here that use a dictionary to make it as a multi-one hot encoding. Basically, you have a bunch of ones and zeros in this dictionary and use that as a representation. And what we wanted to see is just like, okay, so it seems from the past that sparse representations, that orthogonal representations are really good. This VQ-VAE is going to give you sparse representations, is going to give you discrete representations, and orthogonal representations. So would this be effective? It also seems that when we look at big monolithic algorithms like Dreamer, this is one of the components. So how important is that particular aspect to that algorithm? So I had this student, Eden Meyer, working on this, and basically what we're able to show is that first, let's try to learn a model. And what I mean by a model is just like, what I mean by a model is, can I predict what's going to happen next? If I'm in this state and I take another, and I take an action, can I predict what is the next observation that I'm going to see? And one thing that we can see here is that and basically we're looking at 5 steps, 10 steps, 15, 20 steps, up to 30 steps ahead. And when you look at the blue curve, we can see that yes, this discrete representation seems to do really well. But then also, if you have end-to-end representation, sometimes it does well. Like it depends on the different problems that we're looking at. But the point again is that what if we made the environment? We cannot make this environment bigger. So what if we made the neural network smaller? And again, what we see here is that this discrete representation, something like VQ-VAE, when you have much smaller networks, they're still able to do well. While that if you're going to use the standard thing that we do, we need really big networks to be able to solve those problems. And again, if you buy the argument at the beginning of the talk about how we want to be able to solve problems by that are much bigger than the agent, maybe we should be investigating solution methods that are going to be that do well in a lower resource setting, instead of following the traditional way of just making our networks bigger and bigger, because arguably it doesn't matter how big your network is, you're never going to be able to capture all the complexity of the world, and this is just an image of the difference between like some of the predictions that we make and some of the predictions that other systems make. Ours is the one at the bottom, so you can see that it's much more able to predict that I'm going to collect the key and and then open the door and leave the room, instead of other systems that get really stuck into predicting what's going to happen after you go to the door or stuff like that. Okay. This also works, of course, if we want to maximize reward. So what if instead of doing the standard thing, which is to say that what if instead of learning a model, as I was talking about, what if instead of doing this, we said, oh, well, let's maximize the reward directly. And what I'm plotting here is the length of an episode. And in this case, which means that lower is better, because we want to have episodes that are very short, because then I get to the goal state as fast as possible. And what you can see is that the end-to-end traditional solution, as we keep changing the environment, again, really struggles on how to do well. While if we do things that are discrete representations, like the blue curve here, we are able to recover much quicker to these changes. So all in all, that's the main thing that in a sense that's the main message that I wanted to share, which is this notion of like, if we want to do continual learning, and I want to say that we definitely want to be able to do continual learning in AI, I find it a little bit odd that we talk about intelligence, and somehow when people talk about intelligence, they are not thinking about the fact that our systems right now are deployed and they are unable to adapt. And most of the definitions that we have about intelligence, they are related to our ability to adapt on the fly. So I find it a little bit funny that we don't talk so much about continual learning, but at the same time, maybe it's not surprising because when we try to do continual learning, pretty much everything that we need to do, credit assignment, exploration, generalization, is challenged, and the standard solutions that we have, they don't apply. You know, so I see that there is a question on the chat. Fernando is asking whether I have considered KA-ends as an approach to the ReLU issues in that I presented the first part. Uh, I guess I don't know what KA-ends are, so maybe if you can clarify, I can take the question later. Um, but just to wrap up, and then we can open up for questions. Uh, the point again is that continual learning is pretty much required in actually large problems, but we need to revisit the fundamentals of the parallel in order to succeed. We need to be able to assign credit better. We need solutions that are actually thinking about the non-stationarity, and we are the representations that we learn. They don't generalize so well. Okay. All that being said, in the last year or so, we have been making a lot of progress in those problems, and I think that we can do this. We just need to focus and think about more about these problems. Okay. Thank you very much. I'll take questions now. People can feel free to unmute themselves and ask in Portuguese if they want to ask the question, and I can translate the question, or you can ask in the chat, and I'll be monitoring that. Thank you very much. And while I'm waiting for maybe Tel to show up, let me just say that the Fernando got back to me and he told me that what he meant was Kolmogorov Arnold networks, and I have to confess that I have no idea what those are. So no, we didn't try that.
Yeah, this well, Fernando has another question here regarding generalization. Shouldn't the representations also reflect, depend on the topology of the environment, even on its ergodicity?
Yeah. So what we want a representation to do, in a sense, it's interesting, really, because when we talk about this, if we go back, for example, to this slide here that I was telling about the properties, you could think that maybe the topology of the environment would be captured by the dynamic awareness here. And we didn't necessarily see a lot of statistical significant results in terms of like a network that it's able to predict a representation that it's better able to predict the next state will necessarily lead to better performance in terms of generalization. One thing that I didn't talk about here, but it's tied to this notion of where do these options come from, is that we are basically learning this from a representation that does take into consideration the topology of the environment. So, but again, the thing to keep in mind here is that when we are talking about a lot of those problems, we don't know the topology of the environment. So we can try to learn, and sometimes that means that we're trying to be model-based about it, and we're learning a model. But sometimes we're just trying to adapt the value function. So there's a lot of nuance here, but I don't think it's necessarily a bad idea to think about representations that are trying to capture the topology of the environment. And if anything, people often associate my name to a bunch of things related to the Laplacian representation that's doing something very similar to this.
Very good. I have a question myself. Maybe it wasn't clear for me. It's like, what have substantially changed from slides 30 to 31? Um, could you repeat,
so
please?
here, what we were doing here, I guess maybe what you mean is that here, right?
Yes, yes.
So this is we were trying to come from here to here, and this is what we're seeing here. And then halfway through, the world changed, and then we were asked to come from here to here.
Okay.
And then this is the performance of what we get. So this is, but all these curves here are quote unquote baselines. This is like the standard solutions that we have. And then when we go to the slide, all I'm doing is to add the blue curve to give you some context to show that this is how well we can do if we incorporate this idea of adding this ability to these skills to do exploration, you know. And if you pay attention here, I did some really bad cropping because you can even see some of the remaining of the blue curve here because I didn't remove it properly out of laziness.
No problem. But how these reusable skills are implemented? Like how do they? Uh,
Okay,
it's is it
I'm
difficult?
glad that we have another hour to talk about this.
Okay.
Yeah, so this is a question that plagued me honestly since my PhD, and I hinted this here. Like these are the references that discuss this. I this was actually I was debating whether to give this talk or the other or this other talk here,
Okay.
but the notion is I call this a representation-driven option discovery cycle. And what we want is that we're going to be learning representation about the environment. And this representation is going to capture things that we know we can do, but that are hard to do. You know, that's the main thing. I'm just interacting with the environment, and I know that by just interacting with the environment, for example, a child uh, knows that maybe a baby knows that they can move a little bit forward, but that's definitely not easy for a baby to do. But then they realize that they look and say, wait, I can do this. It's hard, but I can do this. So maybe I will try to learn a skill that makes that process consistent. So now how can I learn the skill that allows me to move forward in that way? And then babies arguably learn how to crawl, you know, out of this process. So this is the inspiration. So when we talk about this from a computational perspective, basically we can look at the eigenfunctions of the graph Laplacian. So basically, this comes from graph theory and the graph Laplacian, but the eigenfunctions, they're giving us this notion of how far different states are from each other, with meaning how hard it is to go from one to the other. And then basically, we learn skills that are trying to navigate in the direction that those eigenfunctions are pointing. You know, that's the high level intuition of what's going on. Uh, in a sense, if people are interested about this first reference here, temporal abstraction reinforcement learning with the success representation, it's a 70-page paper that I wrote last year that was supposed to be an introduction to this topic. I love this paper. I force all my students to read this paper. But more than that, it's just like, because it's so long, I feel that we have time to present those concepts in detail instead of the crammed version of the that we have for conference papers, if people are interested in this type of question.
Very good. I'll try to find this paper to share with everyone here in the chat. Meanwhile, we have a question from Fernando as well. He asked, is this learning dependent on message passing, as in MPGNN?
Um, no, no. It's basically we do this with if I understand the question correctly, and GNN is meaning graph neural networks. Um, no, basically we just train with standard gradient descent. We have spent quite some time. Actually, this is the second paper that Diego is my PhD student now, that he wrote his master thesis, which is that he is basically he designed this objective function coming from the graph drawing literature that you can minimize, and we can prove that it converges to estimating the eigenfunctions of the graph Laplacian, and that's what we use to learn that with just standard gradient descent. And thanks for sharing the paper. Uh,
You're welcome. Um, New question from George here. Um, for me, it was not so clear how the environment is always modeled as a graph. Which graph are you using? And if the graph is directed, you don't have the spectrum of the Laplacian, right?
You see, clearly I chose the wrong talk. I chose the wrong talk to give, but I'm happy to use that as an excuse to talk about this thing. So let's think about this here. Let's think about this environment, right? The way that this works is that we can think about each one of these tiles. Let's imagine that here we can actually have in the individual tiles. Just to make it simpler, let's not talk about images for now, but we have generalizations about those things for images and function approximation. We can think about each one of those tiles here as a node in the graph, right? And now we're going to have an edge connecting these different nodes if you can go from one tile to the other. So here basically we have a planar graph that is going to look like this grid world. That's why we love grid world so much, because we can kind of visualize the underlying MDP, which is a graph in a grid world. So that's how we model it as a graph. But just to be clear here, it doesn't have to be a grid world, right? Like if I want to talk about a robot trying to grasp something, it's the same thing. Each state that the agent sees is going to be a node in the graph, and if you go from one state to the other, you have an edge connecting that. So that's the first part. Now, if the graph is directed, I don't have the results here, but this type of approach also seems to work, but of course it impacts the way that you compute the graph Laplacian. We actually have a paper on the works that we have derived an objective that it's specifically tailored to directed graphs instead of undirected graphs. But you still can you can still look at the real values of the eigenspectrum of the graph Laplacian, for example, and that still seems to work really well. And empirically speaking, one of the environments that we had in this paper here that I'm citing, it was something like the agent needs to go to a wall, break the wall, get a key, and then open the door. But by breaking the wall, you cannot put it back. So like the environment isn't necessarily directed, because otherwise you cannot reverse the transition, but it still works. So empirically, it seems to be okay in terms of the directed graph, but also we have some new recent theoretical results that we can do this more in a more principled way for directed graphs. Hopefully I answered your question.
Very good. We have another question from Breno here. Is there any way to understand that the environment distribution has changed and try to adapt the deep neural network to this new distribution?
Yes. So a lot of people have tried this, some notion of some change point detection. And then you say, oh, things have changed, and now I need to and because I know things are changed, I could potentially even reset my network or stuff like that. I don't like that solution. And the reason I don't like that solution is because here we have to be careful. Every time that we're doing an experiment in machine learning and science, I think that quite often people lose sight of the reason we are doing something, the thing that we're doing, right? So here we're talking about this big change. And the reason is just because we want to make a point. It's not because necessarily I fundamentally care about this problem. This is just a proxy for the problem that I'm investigating. And I would say that the problems that we're actually investigating, they rarely you have such an abrupt change. Like the joke that I make, and I actually have a master student working on introducing an environment that has this slow, gradual change instead of these abrupt changes. The joke that I always make is that sometimes this literature on continual learning feels a little bit artificial, because it's as if I snapped my fingers and now you're in Mars. And I'm like, haha, sucker, you don't know how to behave because you're in Mars and you're used to the gravity on Earth. That's not how we do things, right? Like astronauts are going to spend years and years of training, slowly getting adapted to a change on how the world works to be able to perform well in that environment. So in a sense, what does it even mean to say that I can adapt, I can identify that something changed? Because the world is slowly changing, right? Like if you go back to the beginning of this talk, and I come here, right? Like I use different colors to talk about the different seasons, but when we talk about here things here, where did it change? Like here, was it changing? It was clearly getting worse, and then eventually we added a new membrane, and then it definitely changed. But was there a special? Should we have detected changes here? Is this a change? This is a spike? It's hard to define a change, so in that sense, I think that just having this natural gradual adaptation feels much more natural to me than necessarily trying to do this change point detection algorithms.
Okay. Fernando asked one more question here. Behind my previous question, there was another one. Are the reusable skills actually sufficiently local, graph topological features, sufficient to be relatively easier to learn by models?
Well, that's a head herring of a question, because model learning in RL is quite challenging. And when I mean model learning, I mean model based, being able to do planning with learned models. So when you say are sufficient to be relatively easier, uh, it really depends. Um, the graph Laplacian potentially does give you notions of proximity and things like that. It's literally when you go down the eigenspectrum, you're getting different frequencies and things that are close to each other or things that are further apart and stuff like that. So you could very well use that to partition the space in a way that, I don't know, this is a, for example, sorry, but just to be more concrete here, when we look at the second eigenvector of the graph Laplacian, that gives us an estimate on how to do a mean cut in the graph such that we can get components that are independently connected. So now if we think about this, and sometimes people use this in reinforcement learning to talk about bottleneck states. But if we can think about this notion of doing a mean cut, everything that it's on one side of the cut, arguably it's more local than the other one. So you could potentially use some of those ideas to learn local models. Uh, there's a lot of details to get something like that working and some of the assumptions that we want to make. But I definitely think that they can look at the graph Laplacian and some of the properties of the eigenfunctions might be useful in this context.
Very good. We had some awesome questions here, and thanks, Marl, for answering them. It was um, very clear explanation.
Yeah, thank you so much
Um,
for having me. I love an excuse to talk about my work when people are actually willing to pay attention. Because most of the time I'm just babbling and people don't want to pay attention. So it's good when someone is paying attention. And
very
just
good.
because Jorge asked about the paper about the Laplacian, um, it I think that this paper has all the references that you might be interested in uh, this line of work. Sorry, that's the problem with animations. This paper here, this JMLR paper from 2023. So basically, I only have one JMLR paper in 2023, so it's easy to find. My paper in JMLR 2023 has an introduction, a gentle introduction to the topic, but it also has a lot of references for other things. And then if you want something more mathy and more applied to neural networks, the second paper is going to be the way to go about it.
Okay, I send in the chat here as well. Very good, very good. Do we have more questions? Feel free to ask. There's a little bit of a delay to the live, so let's check that.
It's my first time in a live, so I'm enjoying the whole process.
Very good.
Okay. I guess probably that's
Well,
enough. I have answered everyone's questions. Now everyone is it's completely clear everything about this talk.
everything is clear. Um, well, if we have no more questions, I would like to thank you again, Marlos. It was a super clear, a brilliant presentation.
Thank
The
you so much
Institute and
for
the
having me.
university appreciate your participation a lot. We're looking forward to seeing in the future, maybe in the next event. And thank you so much for participating.
Sure. Thank you so much. Have a good day, everyone. Bye.
Bye bye. See you. Um, okay. The next talk will be about ethics in AIs with Nina da Hora. Will be in Portuguese, so check that out. I'll send a link here for the next talk. Um, well, thank you so much for participating in this live. See you in the next one. Thank you so much.